I was supposed to, never mind.
Oh,
Switched
okay.
over already.
Well, good evening, and thanks for being here. Thanks for inviting me, and thanks to Doug for organizing this. You know, Doug, you know probably better than me, Doug is a formidable person, and when he wants something to happen, it happens. And so I'm here, but I'm delighted to be here because talking to MIT groups is one of my favorite things to do. Doug is right. About 3 years ago, I was looking at my iPhone while I was talking, and I'm not going to be doing it tonight because my daughter played last night, and sadly, her team lost. And 3 years ago, she was, or when I was here, she was a freshman. Last night, as a senior, that may be the last game that she plays, which is kind of poignant. But the good news is it's a family night for me because my son Leo is sitting right here, and I'm delighted that he's able to be here. So I have a message for you this evening, and that is that a nuclear revolution is brewing. Not a nuclear renaissance, we've heard a lot about that, but rather a nuclear revolution. And one of the centers of this revolution is Cambridge, Massachusetts. 77 Massachusetts Avenue, to be exact. And I'm going to tell you a little bit about this revolution and the part that we're playing in it at MIT. But first of all, I want to explain why it matters. And Doug talked about the excellent film Pandora's Promise. We had one of the premieres at MIT probably a couple of years ago now. And as Doug mentioned, it describes, and many of you have seen it, how a group of prominent environmentalists who were anti-nuclear changed their minds. And one of the things that caused them to change their minds, I think most of them said this, was climate change, the risks of climate change. But as we all know, many other environmentalists haven't changed their minds and continue to oppose nuclear. And it's interesting to think about why. This is Ralph Cavanaugh from Natural Resources Defense Council, who commented after the movie The Pandora's Promise emerged, when asked, you know, where do things stand in the environmental movement, said this: I have a pretty good idea of where the mainstream groups are on this issue, and I've seen no movement. So it's interesting to think about why that might be. In theory, there are three possible explanations. One is that these people don't think that climate change is a serious enough problem to reconsider their opposition to nuclear. Another is that they do see climate change as a serious problem, but that they also believe that other technologies that they see as preferable to nuclear, like solar and wind, are either already adequate to the need or will soon become so. So that there's no contradiction in advocating for strong climate policies while continuing to oppose nuclear. A third possibility is that they see climate change as a serious risk, but they see nuclear energy as a bigger risk. In that view, the question of whether other ways of addressing climate change will be effective is irrelevant because the nuclear cure is worse than the disease. Of those three explanations, I think we can probably rule out the first possibility, and it's most likely a combination of the second and the third. And certainly there are people who think that we can't afford to have nuclear energy under any circumstances, but I suspect that the other group may actually be larger. The people who are seriously worried about climate change, but who prefer not to have to rely on nuclear energy and think that we'll be able to get by without it. Now, roughly speaking, there are four counter-arguments that, to that view. Namely, that the risks of climate change are bigger than these people think, that the required scale of an effective response to the problem is bigger than they think, that the potential of non-nuclear low-carbon sources isn't as big as they think, and finally, that nuclear isn't as bad as they think. And I'm going to have something to say about all of these things. But let me make the point at the outset that climate isn't the only energy problem that we have to deal with, that the world has to deal with. There are, in fact, at least 4 separate problems, each one of it which is very difficult to solve. The first problem is the rapidly growing global demand for affordable, reliable energy supplies. By the middle of this century, global energy use will likely have increased by at least 50%, and electricity use will have more than doubled. Now, some people look at those numbers and see a troubling picture of human irresponsibility and waste. But let's not forget, and I'm sure most of us don't forget, that we're living through a period in which hundreds of millions of people, actually probably billions of people, in Asia, in Africa, in South America, are lifting themselves out of poverty and starting out on the road to what most of us would recognize as a middle-class standard of living, all within the span of a few decades. That is an achievement that has no precedent in all of human history. One of the consequences is sharply increased energy use. But for anybody who thinks that, say, a doubling of electricity consumption by the year 2050 implies irresponsible, wasteful consumption, it's useful to think about what that actually would mean. Roughly speaking, if electricity demand doubles by the middle part of the century, it's going to mean that the richest billion of the world's population will be using electricity at about the same rate that the average American uses it today, that the middle 7 billion of the world's population will be using electricity at a rate that the average Chinese mainlander uses it today, or about a quarter of the average American's usage, and the poorest billion will still have no electricity at all. That's what a doubling of electricity demand between now and mid-century will mean, and to me, that doesn't seem irresponsible or wasteful. The second problem is that the world's increasing dependence on oil and gas imports to meet that demand will increase economic vulnerabilities, and that will inevitably aggravate international tensions and the potential for conflict. We may be heading for energy independence here in the United States, perhaps, but the rest of the world certainly isn't. The third problem, and Doug already alluded to this, is that fossil fuels, which today account for more than 80% of worldwide energy use, are dirty. Indoor air pollution from the burning of solid fuels, mostly coal and wood, is estimated to account for about 3.5 million deaths per year worldwide, and as many as another 3 million people per year die prematurely from ambient outdoor air pollution. Again, much of it due to the burning of fossil fuels, with 40% of those deaths occurring in China alone. And the fourth problem is that of climate change. How can we meet the rapidly growing need for affordable, reliable, secure energy without wrecking the global climate? Now let me say, and you've heard from Kerry and probably others who are much more knowledgeable about this subject than I am, but let me say that there is still a lot that we don't know about the global climate system, and what we do know is subject to many uncertainties. The scientific debate is not settled by any means, but the debate about the scientific basis for responding to the threat of climate change is settled. Even though we don't have a perfect understanding of the impacts, we know enough to know that we must act. There's still a chance that we'll be lucky and that the consequences won't be as bad as the median risk estimates suggest. but there's also a chance that they'll be much worse. That uncertainty complicates decision-making about what action specifically we should take, but it doesn't change the basic conclusion that action over the next few decades will be needed to avoid a range of dangerous climate-related outcomes that at present seem much more likely than the more benign possibilities. So in my judgment, the problem of climate change and the transition to a low-cost, low-carbon energy system is the most important and most urgent of the world's 4 great energy problems, as well as being the most difficult. But of course, it would be a lot less difficult if we didn't also care about economic growth. In the US, we've actually done pretty well. We've had a pretty successful carbon mitigation policy since 2005. Carbon emissions have been falling. Good for us. But as the latest economic report of the president points out, more than half of those reductions can be attributed to the weak economy that we've had since 2005. We had a much stronger economy during the 1990s, as most people here remember very well. So what would have happened if the economy had continued to grow at the same rate since the year 2000 as it did during the previous decade, instead of about half that rate, which is what actually took place? The answer is that our carbon emissions would be 25% larger today than they actually are. Now, how many people do you know, and more specifically, how many politicians do you know who would voluntarily forego an extra $3 trillion in annual economic output for a 25% reduction in carbon emissions? It is what happened, but I bet we wouldn't have chosen to do it. The bottom line here is it's not either or. We, and even more the rest of the world, need less carbon and more economic growth. So here's a chart that makes the same point at the global level. What you're seeing here is the historical correlation between carbon emissions, carbon dioxide emissions per capita, it's 3-year averaged, plotted against GDP, economic output per capita, for a bunch of different countries, and each of those lines is 50 data points, 50 years of annual economic output and annual carbon emissions per capita. So the line for each country, this is the United States. This light blue one, I'm sorry, that orange one is Canada. This one, the light blue one, is Japan, and so on. Broadly speaking, what this chart tells us is that the world is moving up and to the right. In other words, we consume more in economic output, we emit more carbon emissions. Although there is some flattening, clearly, as at least in the richer countries, but it's a much steeper slope, generally speaking, among the poorer ones. If we want to address climate change effectively, we have to decouple economic growth from emissions. We cannot do this by running history backwards and going down and to the left. That's actually what if you see these little things here, that's what we have been doing for the last few years since the Great Recession started. But that is not an acceptable long-term strategy for this problem. And it isn't enough to flatten out, as the chart suggests is happening as countries get richer. We have to convert the general trend line in this chart to something that looks like that. And in other words, less carbon and more economic growth. And the only way to do this is to reduce the carbon intensity of the global economy. So we have 2 ways to do this. We can decarbonize the global energy system, get carbon out of the energy supply system, and we can reduce the energy intensity of our global economy. In other words, use less energy per unit of economic output. How much of these two things are we going to need? Well, here's where we are today, which shows a globally averaged annual rate of carbon emissions per capita of about 4.2 or 4.3 tons of carbon dioxide per year, or about 1.25 tons per person of carbon per year. This average is below most of the lines on this chart because most of the world's population is at the lower end. That's where China and India and so on are. Where we need to go depends on the climate mitigation goal. And here we can look at two illustrative mitigation scenarios from the latest assessment of the IPCC, the Intergovernmental Panel on Climate Change, which has been released in pieces over the last several months. One of these scenarios, the most stringent one analyzed, is associated with an 80% probability that the global surface average temperature increase will remain below 2 degrees C at the end of this century. Now that goal, 2 degrees C increase, is the goal that many governments have notionally adopted, including our own government, or at least our own administration. It's roughly equivalent to an equilibrium atmospheric concentration of carbon dioxide of 450 parts per million. We're closing in on that pretty quickly. In the second scenario, a less stringent scenario, there's an 80% chance that the end of century temperature increase will exceed 3.1 degrees C. That's roughly equivalent to a doubling of the atmospheric concentration of carbon dioxide, 550 parts per million relative to pre-industrial levels. Most climate scientists, and many others too, would regard that target as being insufficient. The global average per capita emissions in the year 2050 that are associated with those two scenarios are shown in these two lines. The green one is the 2 degrees C scenario, and the black one is the 3 degrees scenario. That's where we would have to be in terms of global average emissions per capita in the year 2050. Now, suppose we say that the emissions of every country, whether you're a rich country or a poor country, should converge to that global average per capita emission rate by the year 2050. Now, a lot of people would see that it sounds like an equitable goal, right? Every country does the same by 2050. Many people might see that as equitable, but there are certainly many others, especially in the poorer countries, who would not see that as equitable at all, given that the rich countries obviously were responsible for most of the carbon emissions until now. But we also know that the poorer countries will be responsible for most of the carbon emissions going forward, and so maybe that might become the basis for some sort of global agreement. If the US were to agree to it, the 2 degrees C scenario would require us to reduce our emissions by about 90% between now and the year 2050. If we signed up to a 3 degrees C target, which remember many people view as being, and certainly most climate scientists view as being inadequate, that would still require us to reduce our carbon emissions by about 70%. So that's how much we're talking about. Charts like this are informative, but lines on a graph can't really convey how difficult this is going to be. So here's another chart, some of you may have seen it before, which shows where in the economy our carbon comes from. Each of these little squares is 10 million tons of carbon dioxide per year. And there are 726 of them. Even for the less stringent 3 degrees C scenario, which as I've noted, many would regard as inadequate, we'd have to eliminate 70% of these squares by the year 2050, while meeting the energy needs not only of the current economy, but by the year 2050, a whole additional US-sized economy that we're going to be adding between now and then, even assuming a relatively modest 2% per capita economic growth rate, which is not that one that we would necessarily be hugely enthusiastic about, although it's better than we've had for the last 15 years. It's also instructive to think about the physical scale of this task. Again, these sorts of things don't quite capture it. Let's consider coal, which accounts for about a third of our carbon emissions in this country and about 75% of the emissions from the electric power industry. If, say, we put all of the coal that all of those coal-fired power plants use in a single year, and we put all that coal onto a single coal train that went round all the coal plants, delivered the coal for a year, that coal train would be 85,000 miles long. And if we want to achieve even the more modest 70% emission reduction goal, essentially all of that coal would have to be replaced. Or we might alternatively capture the carbon dioxide from the coal plant. Now, by the way, if all of that coal were replaced by natural gas, which we have been doing, some of it in recent years, that's actually stopped recently, but there was a period when we were replacing coal with natural gas. If we replaced all of the coal plants with natural gas-fired plants, total US emissions would decline by about 20%. It's a very important contribution, to be sure, but not even a third of what would be needed even in the less aggressive 3 degrees C scenario. So that's a few points about the scale of this task. Now, the next question is, can we do this without nuclear? I mean, one question is, can we do it at all? But we might also ask, can we do it without nuclear? Because that's kind of tonight's subject. I can't prove the answer to you in any mathematical sense, but I think it's a matter of basic common sense that when you have a very difficult task like this, the more options that are available, the more likely you are to succeed. And if any option is taken off the table, the chances of failing will increase. And that's especially so because no two low-carbon options are alike. Solar, wind, geothermal, and nuclear each have their own strengths and weaknesses. And here, I just want to mention a couple of points about nuclear advantages of nuclear that seem to me not even fully appreciated even today. One of them is the extreme compactness of nuclear energy systems. For example, that same thought experiment that gave us the 85,000 mile long coal train would yield a 1 mile long nuclear train. That's the length of the train. If we loaded all of the nuclear fuel that we need to fuel our 100 nuclear power plants that provide 20% of our electricity, put all that fuel on a single train, had it go around the 100 nuclear plants, for a year, it would be 1 mile long. The second aspect that people, I think, don't fully appreciate is the ability of nuclear power programs to scale up quickly. Now, scaling up, rapid scale up, is really in some sense the name of the game here. If we're going to meet these extraordinarily ambitious carbon mitigation goals, it's going to depend on how quickly we can scale up low carbon energy sources. Now, there's a popular view that we can build out wind and solar very quickly. And indeed, it's relatively easy to build new wind turbines and put solar on our roofs and so on. But if you look at the historical facts, it's nuclear energy that has actually scaled up the fastest. Remember this chart, the down and to the right chart. It's very hard to see here, but there are a couple of examples of countries that did move down and to the right. France is this one here, which went down and to the right during the 1970s and 80s. Its economy was kind of doing okay, not great, but it was doing okay. But it went down in its carbon, per capita carbon. Why? Because they built all those nuclear plants very fast during that period. Japan is another example here. And the next figure adds to the story. It shows that the amount of carbon mitigation achieved in countries like Sweden and France and Belgium and so on during the peak decades of nuclear construction in the 1970s and 80s, when nobody was really thinking about carbon, but they were actually thinking about other issues, energy security and so on. But the rate at which we added zero carbon electricity in megawatt hours per capita during those peak decades was far greater than what we're now adding with countries like Denmark and Spain, which are very aggressively adding, deploying solar and wind, have been more recently. And in Germany, which of course is now phasing out its nuclear plants, when those plants were first phased in, here, they were adding low carbon electricity twice as fast as the big solar and wind programs are adding them today. And here in the US, when we were building nuclear plants during the 1980s, and actually the 1970s would be even more so, we were adding low carbon megawatt hours per capita 4 times faster than we have been doing in the most recent decade. So far then, nothing compares to nuclear when it comes to rapid scale-up of low carbon energy, which remember is the key to being able to address this carbon issue. Obviously, nuclear is facing severe headwinds in many parts of the world today. I'm not going to go into detail, but I do want to say something about Germany. Doug mentioned it. We have the Energiewende, the transition to a solar and wind dominated economy. As recently has been pointed out by a number of people, if you think that the Energiewende is the solution that Germany has adopted for climate change, think again. Think again. Let there be no mistake. The first priority is to use that solar and wind capacity to retire the zero carbon nuclear fleet. And only when that has been accomplished will the Germans pay attention to the fossil fuel plants. And in fact, as Doug mentioned, German carbon dioxide emissions have been rising. So what the Germans are doing, very simply, is putting nuclear phase out ahead of action on climate change. And also ahead of the case for reducing the other adverse effects of coal use in Germany. And here we're talking about thousands, many thousands of premature fatalities. That's a choice that makes no sense except as an ideological policy. Now, for more understandable reasons, the Japanese have made a similar choice, at least for now. All of Japan's nuclear plants have been shut down, and as a consequence, Japanese imports of coal and gas and its carbon emissions have both risen sharply. There are moves to restart some of the reactors, but I think it's very unlikely that more than about half of them will eventually be restarted. Here in the US, where we still generate 1 out of every 3 nuclear kilowatt hours anywhere in the world, we're building 4 new plants, but several others are closing. And I think of greater significance, the bulk of the 100-reactor US nuclear fleet, which still provides us with almost 2/3 of our low-carbon electricity, 5 times more than wind and solar combined, that fleet will begin to be phased out starting in about 15 years, and there are no plans to replace those reactors. Of course, there are ambitious programs in some countries, most notably in China, also India, Russia, Korea, and a growing number of newcomer countries are entering the nuclear energy field for the first time. Countries like the UAE, Saudi Arabia, Turkey, Vietnam, Bangladesh, maybe a dozen others. But if you add up all these plans, take all those countries that have plans, and in both the newcomer countries and the existing nuclear countries, the fact is, and you can do the arithmetic, the additional nuclear commitment isn't large enough to have a big impact when it comes to reducing the world's carbon emissions. And when you combine that with the expected retirement of much of the existing nuclear fleet as those plants reach their end of life, and the average age of the world's nuclear fleet is about 30 years. 30-year-olds here don't seem very old, but a nuclear plant that's 30 years old is getting a little long in the tooth. If you combine all of that, the nuclear contribution to carbon mitigation seems today as likely to shrink as it does to grow. And so here is the puzzle. Here's the puzzle. On the one hand, the world has little or no chance of maintaining even a modest rate of economic growth while avoiding the worst risks of climate change without a large-scale expansion of nuclear energy. On the other hand, if you look at what the world's actually planning to do about nuclear energy today, it doesn't add up. And so the question, and I think this is the most important question for nuclear energy today, is how to close the gap between nuclear needs at the global level and nuclear plans. Well, one possible answer is just stay the course. Hang in there. Eventually, the rest of the world will catch up to the Chinese, figure out the view in China and a few other countries is correct, that nuclear energy is an attractive alternative, especially once the full costs of burning fossil fuels, including the environmental costs, are charged to energy users, which, by the way, the Chinese are very likely to implement before we do here in the United States. So that's one view. But there's another view, a different view, which is that business as usual won't be enough. And that while pricing or taxing carbon and the other externalities of fossil fuels will help the competitive position of nuclear, much more will need to be done to close the gap. In this view, if nuclear is to realize its potential to help drive the transition to a low-carbon economy, a technology that's already much safer than it was when the first commercial reactors were built more than 40 years ago will need to be made safer still, less expensive, more secure against the threats of nuclear proliferation and terrorism, better suited to the evolving capabilities and limitations of power grids and the utilities that operate them, and better able to provide low-carbon energy inputs for a broad range of applications beyond the conventional baseload electricity generation. In this view, in this second view, which I share, innovations of all kinds will be needed, technical and non-technical alike, especially innovations in nuclear governance, innovations in education and training to address the urgent need to replenish and strengthen the nuclear workforce, and innovations in nuclear technology. I want to focus on the last of these three, but all of them are important, and let me just say a few words about the question of nuclear governance. What's the most important lesson to be learned from Fukushima? The most important lesson to be learned from Fukushima, as well as Chernobyl and 3 Mile Island before them, or before it, is that what might otherwise have been serious but manageable accidents were transformed into disasters by multiple failures of governance. We know very well what will help to fix these, including transparent decision-making, independent regulatory bodies, and the overwhelming importance of building and sustaining a safety culture in nuclear operating organizations. But we also know that achieving those things is going to require much more capable institutions, especially international institutions, than we now have, and that will take a high level of organizational and political innovation. But what about this one? What about innovations in nuclear technology? You know, for many decades, the main goal of nuclear innovation efforts around the world was to conserve uranium, to save uranium, to extend the uranium resource base. And the main focus of those efforts was on the development of advanced converter and breeder reactors to do it. Today, though, other goals have become much more important. Reducing cost, improving safety, reducing the burden of nuclear waste disposal, controlling the threat of nuclear terrorism, making siting of nuclear facilities easier, anticipating changes in the way electricity is going to be delivered to customers, and reducing nuclear cycle times, which have become almost pathologically long in many parts of the world. We can't predict the long-term development trajectory for nuclear, but we can certainly speculate in an intelligent way. For example, we might expect that future nuclear plant designs will place increased reliance on passive safety mechanisms. The new generation of light water reactors has moved in this direction, but other designs go much further toward the goal of walk-away safety. It doesn't seem far-fetched to suggest that such a goal of walk-away safety will become a requirement for all nuclear reactors 30 years or 50 years from now. On the question of how to reduce lead times, well, some people focus on regulatory reform, but there are also opportunities for technically driven cycle time reductions. For example, enormous advances are occurring in modeling and simulation of neutronics, thermal hydraulics, and fuel behavior, enabled by the next generation of supercomputers, and these are making possible much faster and more efficient approaches to reactor design. New construction methods also promise to shorten project lead times, as do smaller and modular reactor designs, which have other hoped-for benefits too, including reduced capital at risk, faster learning cycles, and so on. Related to this, power grids and power markets are likely to undergo changes over the next couple of decades that may be more far-reaching than any we've seen in the last 100 years. There are people who even suggest that the centrally controlled power grid will go away and will be replaced by decentralized, customer-driven local networks. I think myself that that's an exaggerated view, but we're surely going to see further penetration by non-dispatchable solar and wind, both at the utility scale and in smaller scale decentralized deployments. We'll see more local microgrid operating systems, new roles for intelligent grid technologies, web-connected electrical devices, large-scale data analytics, and plenty more. And one of the challenges here is going to be to work out how to meet rapidly changing electrical loads affordably and reliably with low-carbon power systems that may ultimately consist mainly of reliable, dispatchable nuclear and non-dispatchable renewables. I'll have more to say about that in a minute. Other innovations will focus on new siting strategies. Again, a little bit more about this in a minute. Maybe we'll see other possibilities, such as lifetime fueling of reactor cores, the so-called nuclear battery concept, and integrated power plant waste disposal systems with spent fuel never leaving the power plant boundary and disposed of directly in modular deep boreholes several miles below the Earth's surface in the stable, dry bedrock that's abundant in most countries. Maybe we'll have reactors optimized for burning nuclear waste, transmuting the long-lived or longest-lived isotopes in the waste into shorter-lived species. Another possibility is that advances in computational power and new tools for material synthesis one day might make it possible to design and build radiation-resistant materials from the ground up, atom by atom, and to create ultra-secure nuclear waste materials with lifetimes of tens of thousands of years. All of these developments can be imagined today, and surely much greater advances lie over the horizon. And the point I want to make here is simply that when it comes to nuclear innovation, I think we're really only at the beginning. And let me remind you in this regard that it's still only 75 years since the nuclear fission reaction was first demonstrated. Chronologically, that puts the field of nuclear engineering today roughly where the field of electrical engineering was in the year 1900, a few decades after the great discoveries in electromagnetism and electrochemistry by Faraday and Maxwell and Gauss and the others. Think about what the electrical engineers achieved in the subsequent decades. The creation of the electric power grid, the radio, television, the revolutions in microelectronics, computation, telecommunications, the internet, and all those other things. An astonishing series of advances, not one of which was anticipated by the electrical engineers of the year 1900, or for that matter, by anyone else. And likewise, today, nobody can foresee the range of practical applications of nuclear science and technology at the end of the 21st century. So what are we doing about all of this at MIT? Well, I hope you got your baseball cards. Because if you look, this is our brochure, the NSC brochure. We don't have one. We have these. By the way, I actually thought that this would be a good idea, partly because I thought it might be a good alternative to the course evaluations. Because I thought maybe a market might develop in these. You know, you could have three Lesters for a Todrius. Somebody asked about Todrius. It didn't, so far at least, no evidence of a market has emerged among the students, but they're fun anyway. But I want to mention just 3 ongoing areas of research in the department, each one of which has the potential to change the game for nuclear. And I'm going to be very brief because I want to make sure we have time for questions. Here's the FHR project. This stands for Fluoride Salt-Cooled High-Temperature Reactor project. It's a concept for a small, modular, load-following, high-temperature, low-carbon, nuclear hybrid electric power system. It's been developed by a team at MIT in our department led by Charles Forsberg in collaboration with teams at Berkeley and Wisconsin. And the question here that they're interested in is, if you want to have a low-carbon world, you're going to have to remove most of the carbon from the electric power grid. And some people have suggested that we can rely on renewables plus storage, which of course we don't have yet. So perhaps we'll need backup generating capacity, probably gas and maybe a lot of it. And indeed, in Texas, where they have a lot of wind, only 8% of the wind capacity there can be assigned as dispatchable, which implies that in Texas, for every 100 megawatts of wind, you need about 920 megawatts of backup capacity for when the wind doesn't blow. In the Midwest, it's a little better. 13% of the wind capacity can be assigned as dispatchable, but still you need a lot of backup. So that's one scenario. Another is that we can have a combination of renewables and nuclear, possibly with less gas and possibly with less backup. But the kind of power market that we're talking about is going to be very different from anything that nuclear plants have been serving until now. Here's what the market, so this is the power market in the New England, the Boston part of the New England region. That's over a year, and clearly if you just had nuclear and renewables, you couldn't satisfy that profile. We're heading in the direction of more solar and more wind, and what that means is that the low cost or the low price tail and the high price tail of electricity are going to get longer and fatter because of the presence of solar and wind. When the wind blows, when the sun shines, we end up with surplus amounts of electricity which goes for a very low price, even possibly in some cases a negative price. And if you have, and of course when the wind and sun aren't operating, you have very high price electricity. But the problem, if you're a capital intensive power plant like a nuclear plant or like a solar and wind plant, is that when the price is very low, it's really going to hurt your economics because you need to keep those things operating all the time in order to get your capital back. So what's happening, as you probably are well aware, is that in some power markets, and this will become more prevalent as sun and wind increase their output, revenue is collapsing, and that's pretty tough for capital-intensive, particularly baseload power plants. So to address these issues, the FHR team is exploring combining a nuclear plant, in this case a fluoride salt-cooled plant, with a natural gas booster, combining it with natural gas. The nuke runs at steady state in baseload mode. It heats compressed air, which is run through a standard GE turbine, frame 7 turbine, to produce power, 100 megawatts of power in this case. And when you need more power, you augment the heated compressed air with the combustion products of natural gas. It's a very fast, you can get very fast response, no cold start needed because the gas is going into an already hot turbine. It's actually a very efficient use of natural gas, 67% combustion efficiency compared with 60% today in the best conventional combined cycle plants. And in this system, you can augment the 100 megawatts of nuclear by another, at the peak, 142 megawatts of natural gas-fired electricity with no need for a backup generator. With this kind of system, the nuclear plant makes a lot more money. Here is, let me see, well, I guess I don't have, yeah, here's what happens. This is a simulation for the Texas market and the California market. Without, just running a baseload plant, which is what one would do today, if that's the benchmark, 100 units, if you run the plant in conjunction with a natural gas peaker using the same frame 7 turbine, after you've paid off the natural gas cost, you can increase the revenue flow to the nuclear plant by 42% in Texas and 67% in California. So that's actually a very, potentially a very attractive possibility. Of course, you've got to look at the cost side, and the group is still working on that. One of the constraints that they set themselves was to rely on existing technology. And so this new reactor concept uses coated particle fuel that was originally developed for HTGRs and that is being manufactured in China. Today, it uses liquid salt coolant. That's the transparent coolant you can see there. And it uses a commercially available frame 7 turbine. There are all sorts of other tricks that they're looking at, including using heat storage systems, fire brick heat storage systems, not fancy batteries or anything like that, but just heating up a fire brick. It turns out that this looks quite interesting, quite attractive, and we've been doing it for more than 100 years. The group is looking at, is using our MIT reactor. We have a 6 megawatt reactor there on Albany Street. Some of you will remember it. It was there 56 years ago. It's still there. And we're using it to do irradiation experiments on some of the materials. This is not without challenges. You're going to produce tritium in this reactor, which is hard to manage, hard to keep track of. And also, molten salt is not the best environment for other materials to do well in. So we're working on this, and we're being sponsored to do this, by the way, by the Chinese, who are going ahead with this technology a lot faster than we are. We have about a $7 million program sponsored by the Department of Energy. The Chinese have a $1 billion program on this technology. They've got about 600 or 700 engineers that they've assigned to the development of this. They're building 2 prototype reactors. Probably they'll be ready by the year 2020. But in the meantime, they're coming to us to do irradiation experiments in our reactor because they have no way to do them. Okay, very quickly, another development, the offshore floating nuclear power plant. You may have heard something about this. It's motivated by the desire to reduce capital costs, but also to address safety and security concerns since Fukushima and 9/11. You want to site power plants near the coast because that's where most people live, but you don't want to use valuable real estate if possible. So here's an idea that's being developed by a team led by Jacopo Buongiorno, one of our faculty members, which combines 2 mature technologies, oil and gas drilling rig technology with, in this case, a small modular nuclear reactor to build the reactor in a shipyard, the way we build reactors today for the submarines, and transport it to the site and maybe 5 or 6 miles offshore in deep water where there's not an earthquake or tsunami concern, and with the nuclear plant suspended under water, you of course have an infinite heat sink and don't have the problem that the Fukushima reactors ran into where they lost their heat sink, nor do you have a tsunami concern at those depths. The reactor would be connected to the grid by a transmission line. The problem of thermal pollution would go away because of the opportunity to bring water in from lower, colder layers of the ocean. And in principle, you could do this with reactors of any size because the size requirement of these offshore rigs is actually quite a bit smaller than the largest oil and gas drilling rigs that we're building today. There are many issues here, including security. How do you maintain the security for a floating nuclear power plant? The team is working with various experts on this issue. It's not what the Russians are doing, where you've got an icebreaker on a barge, or a reactor, icebreaker reactor on a barge, and you dock the thing in a port. That's what they're talking about. The French are talking about sinking a submarine onto the seabed. Westinghouse years ago talked about a huge breakwater surrounding a nuclear plant in shallow waters. This is a different concept. It's a very different concept. It's a paradigm shift in how to design, build, and operate a nuclear plant. Deep borehole disposal of nuclear waste. Professor Driscoll has been working on this problem for 20 years. There has been no funding of advanced technology for nuclear waste disposal by the US government for 25 years. No research and development funding. Congress actually prohibited it in legislation that was enacted in 1987 when they chose Yucca Mountain. Here is a different approach, 10 times deeper than the mined repository would be at Yucca Mountain. Lots of technology to draw on from the oil and gas industry, for whom a 4 or 5 kilometer deep hole at this point is trivial. There are tens of thousands of such holes drilled every year. One of the attractive features of this scheme, which is to lower the canisters into a deep hole and backfill the top 1 or 2 kilometers with various forms of concrete and other kinds of backfill. One of the nice features of this is its modularity. You can drill a hole, and if it turns out you're in the wrong place, you can walk away having spent maybe $30 million as opposed to the $15 billion that we've already spent on Yucca Mountain before deciding, maybe we'll change our minds, that it's not a good place. It's extremely remote probability of intrusion. Plutonium mining is very unlikely at those kinds of depths. This may be particularly attractive for small countries in seismically active regions. Okay, I'm going to skip what I wanted to say about the rebuilding of the department, but let me just very briefly say that this is a period of very rapid change in our department. Not only are these kinds of research projects going on, but in the last 5 years, in a very real sense, we've been reborn. Despite having Fukushima in the middle of it, it hurt us, but we've stayed pretty much on track. We're the smallest engineering department at MIT, but we're growing. We have a lot of new faculty. We're now the youngest faculty at MIT. By a large margin, the median age of our faculty is 37. The median age of the MIT faculty is over 50. More students are coming into the department. We still have a very small department, but we took in more graduate students this year than we ever have in the last 40 years. Research volume has doubled since 2010. We're also introducing a new curriculum. In short, there's a lot going on in the department. The next task that we have is to rebuild our infrastructure. We have remarkable assets. We have 2 operating nuclear reactors in Cambridge, Massachusetts on Albany Street. I mean, it is really quite remarkable. But a lot of that infrastructure is still in the 1960s. We need to upgrade the reactors. One is a fission reactor, the other is a fusion reactor. And we want to build a new complex of teaching and research labs and incubator space where we can bring new companies, continue to spin out our own companies, and where we can help to build the future of the field. So if anyone is interested in this set of activities, we'd be delighted to talk to you about them. Let me finish with one thought. It's become common among politicians and pundits to predict the end of nuclear power and argue that it's just too difficult, it's not worth the trouble. But I think that there's a different and actually more plausible view of the nuclear future, and that is that the nuclear era, is only just beginning, and that the most important innovations of the next several decades won't be the ones that we've been talking about for the last several decades, and that a lot of people are still talking about today. And so, finally, I think we have a really important choice in the United States today, now. We can either continue on the path we're on, which very quickly, quicker than most people I think recognize, will lead to the status of being a nuclear also-ran. That's the path we're on. Or we can tap into the enormous entrepreneurial and innovative strengths of our economy and lead this globally important industry in new directions that will make it a far more effective weapon in the fight against climate change than it is today. Thank you.